So when we last talked, we had the class equation. And one of my favorite corollaries of the class equation is the fact that if you have a group of order p to the n, so it's just a prime power, then it's got a non-trivial center, right? So there's at least one non-identity element that competes with everything in the group. Here is a consequence, yet another cool consequence. We have classified all groups of order p, right? Where p is prime. In fact, can anybody tell me, if I walk up to you on the street and I give you a group that is of prime order, what can you tell me for sure? Right, cyclic. It has to be isomorphic CP because it has to have an element of order P. That element of order P generates a subgroup of order P, but that's got to be the whole thing, right? This goes a step further, doesn't classify them, but one thing that we do know is any group of order P squared has to be abelian. So if you have a prime power order group and A is 0, 1, 2, where A is the exponent, it has to be abelian. A to the 0, no mystery, because that's the identity group, right? A to the if A is 1, P to the 1, that's group order P, so it's cyclic. 2 is the interesting case. So let's do a proof for A. And I will appeal to an old homework problem too. So this is just nostalgia morning. If the order of P squared, let CG be the center of G. So what do we know about the order of the center? Well, the center is a subgroup, right? So the order of the center has to divide P squared. So what are the divisors of P squared? 1, P squared, right? But the center of G is not equal to the identity. So the order of the center of G is equal to P or P squared. Agreed? That's it. Has to be one of those two. Everybody agree with that? This is that corollary that any P group has a non-trivial center. So I've got two cases here. Which one of these cases leads to an immediate conclusion?
It's P, it has to be greater than 2.
Well, let me ask you this. What happens if the order of the center is P squared? What does that mean? That means that the center has to be the entire group, right? Which means that it's abelian. If the order of the center is P squared, then G is equal to its own center. So abelian. Right? Okay, so the only thing we have to worry about now is, okay, then, so what if the order of the center is just P? Well, note that the center of G is a normal subgroup of G. This is always true, right? So let's see if anybody remembers the homework problem. If the order of the center of G, P, then the order of G mod CG, what is that going to be? Well, what's the order of G? P squared. What's the order of center? In this case, P. Everybody okay with it? So what can we conclude about this? This group is of order P, so it must be cyclic. Anybody remember the homework problem? G is abelian if and only if G mod CG cyclic. And there you go. In this case, if the order of the center is P and the order of the group is P squared, the quotient group has order P, is therefore cyclic. Therefore, G is abelian. There we go. So that's step 2. We will see later, actually, that if you have a group of order P, it's cyclic of order P. There are actually 2 different groups up to isomorphism of order P squared, you will see lately. ZP and the direct product of ZP, ZP squared, so cyclic of order P squared, and ZP direct product with itself. Do you know how many groups of order P cubed there are up to isomorphism? That one's a little trickier, right? It turns out that if you have a group of order P cubed, there's 5 things that can happen. There's 3 of them are abelian, 2 of them are non-abelian. How do you even open up that can of worms? Well, we're fixing to do something here that's going to help and this is actually one of the biggest tools in finite group theory. So we are going to discuss the very famous Sylow theorem, which will allow us to understand the structure of more complicated. So let's hit this. Sylow theorems. Before I stampede off into Sylow land, let me give you a definition first. So definition. Let's let G be a group and P a positive product. So some prime integer. Number 1, a group in which each element has order P to the n or some n is called a P group. So what it means to be a P group is if you have any element in that group, there's 2 things that are kind of implicit in here. Number 1, that element has finite order. And number 2, that finite order is a perfect prime power, right? So you might have one element that has order P cubed, another one that has order P to the 17th, but everything in there has prime power order. If G is a finite P group, then the order of G is equal to P to the n, capital N. Okay, there's a number 2 to this, but I want to discuss this first. Why is that? Why is it the case that if you have a P group Why does it have to have order P to the N? Can anybody tell me? Now, here's my confusion. I know that every single element in G has prime power order for some P. And I know that the order of the group is P to the N power. But how do I know that the number of elements in the group has to be a perfect prime power? Why can't it have another prime dividing it? Yes.
It has something to do with the fact that the order of an element has to divide the order of the group.
That's right. And also Cauchy's theorem, right? But that's exactly right. Suppose it's not a prime power order, right? Suppose G were not. That means that there's a different prime that has to divide the order. Everybody agree with that? Some other different prime. We'll call it Q, right? But if Q, that different prime divides the order of G, then there must be an element by Cauchy in that group of order Q, right? And that's a contradiction because we assume that every element has order P to the N power, right? So you can't have a different row Q, right? So Cauchy's theorem guarantees that this is true. Yes.
One more time, the N could be different elements, right? It's just.
That's right.
But the P stays the same.
That's right.
Okay.
That's right. Yeah, the N can vary. This N can vary for different elements, but it's always just the same P. If the order of G is P to the A times M, some A greater than or equal to 1, and GCD PM equals 1. So in other words, suppose I have a group and it's a finite group. What I've done is the order of G is P to the AM, and I've sucked all the powers of P out of this that I can. So there's no other power of P that divides in, right? Then a subgroup of G of order P to the A is called a Sylow P subgroup of G. And it is a maximal P subgroup of G. So if you have a group of order P to the AM and you've exhausted all the powers of P that you can, any subgroup of G of the order P to the A, and P to the A is the biggest power of P subgroup that you could have, right? Because any subgroup has to have order dividing this. So P to the A is as good as it gets, right? If you have a subgroup of order P to the A, it is called a Sylow P subgroup of G. So it's a maximal P subgroup. Notice that in this definition, I don't claim that a Sylow P subgroup exists. I just claim that if there is one, this is what we call it. But they do. And we will see this in states in the Sylow theorems. So here's my strategy. I'm going to give you the Sylow theorems. I'm going to do my best to kind of explain it a little bit. And then I'm going to use it for a couple of small examples. Then I'm going to prove it. That's going to take a little while. And then I'm going to come back and use it for some maybe a little bit more sophisticated examples. Okay, so let's get these famous Sylow theorems out of the way here. Theorem 6.2. Sylow theorems. So here we're assuming that the group is finite. So let's suppose the order of G is P to the A times M, where the greatest common divisor of A and M is equal to 1. So in other words, I've pulled all the factors of P out of this that I can, and A is at least 1. So that. I think you can do this without 0, but statements are all trivial. Number 1, G has at least one Sylow E subgroup. This is kind of the general analog that we had to Cauchy's theorem. So what we know so far in this class is since P divides the order of the group, Cauchy's theorem tells us that there is a element of order P in here. Sylow tells us more. It says, hey, we have a subgroup of order P to the A, right? And by the way, one of your homework problems is number 2 on your homework this week. You know this business about if you have a group of order P to the N, then there's a subgroup of order P to the K inside it, blah, blah, blah. That means not only do I have a subgroup of order P to the A, but I have sort of P to the A minus 1, P to the A minus 2, all the way down, right? But only the big one is the one we call the Sylow group. That is P to the full A power. Number 2, if P is a Sylow P subgroup of G, and Q is any P subgroup of G. Yes.
Over there, you have GCD AM, but over there, you have GCD PM. Is that on purpose?
Oh, yeah, it's a total typo. I'm sorry. Thank you very much. Yeah, I didn't even pay attention. Well, this definitely should be GCD. Yeah, absolutely. That I didn't mean to write A. That should be a P for sure. And it's not she can credit. So suppose P is a Sylow P subgroup of G and Q any other P subgroup, right? I don't claim that this is a Sylow P subgroup. It's just some subgroup of order P to some power A or less. Then there exists a G and G such that Q is contained in GP G inverse. So in other words, if I walk up to you on the street and give you a Sylow P subgroup, one of these max ones, and then there's some other P subgroup sitting somewhere in there, then I can conjugate this so it contains Q. If P contains Q already, then I could take this to be the identity. If not, I can find a suitable G that conjugates this. So one of the conjugates of this contains Q. So in particular, any 2 Sylow E subgroups are conjugate. Right? Because in fact, if this is a group of order P to the A, and it's contained in this conjugate, which also has P to the A, then these two have to be equal. So what that means is there's at least one P Sylow subgroup or Sylow P subgroup. And if there's more than one, pick any, if there's more than one Sylow P subgroup, pick any 2 of them, P1 and P2. P1 and P2 are conjugate. I can conjugate P1 to get P2. Fantastic. And I can count in the following sense. If N is the number of Sylow P subgroups of G, then N is equivalent to 1 mod E. That is an amazing theorem. And I can go any farther than that. Additionally, N is the index of the normalizer of a Sylow P subgroup P and G. So that is to say, N is equal to so N divides M. So that tells me two things. It tells me the number of Sylow P subgroups is equivalent to 1 mod P, and it divides this leftover M here, which is really, really cool. So we need to, it is a moral imperative that we prove this, but before we get too enamored in that aspect of it, let's do some examples. Here's some applications. So here's a first application. I want to understand what every possible group of order 15 looks like. This can be kind of a tricky problem. How many groups of order 12 are there? There's 5 different possibilities, as a matter of fact. For 10, there's 2. For 16, I believe there's 14 possibilities, right? How many are there for 15? Suppose that the order of G is 15, which is equal to 3 times 5. Okay, so far. Let us count the number of Sylow subgroups. Number of Sylow 3 groups. And we'll let N5 equal number of Sylow 5 subgroups. Okay, let's see if we can play Dick Tracy here and use our detective abilities to find out what these are. N3 is equivalent to 1 mod 3. That's what Sylow part 3 says. Everybody agree with that? So N3 are numbers like 1 and 4 and 7 and 10, so forth, anything equivalent to 1 mod 3. But there's another caveat. It has to divide M, which in this case is what's left over, which is 5. Anybody tell me what M3 is? What positive integer is equivalent to 1 mod 3, but also divides 5? Only 1, right? Right? Because the only divisors of 5 are 1 and 5 is not equivalent to 1 mod 3, so it's got to be 1. That means there's only one Sylow 3 group. That Sylow 3 group is of order 3. There's only one. And if you look at this part of the Sylow theorems, that means it's normal, right? Because any conjugate of that is also a group of order 3, but there's only one of them. So there's only one place to go. But that doesn't matter so much at this point. Same for this. Sort of a little role reversal there. The number of Sylow 5 groups is equivalent to 1 mod 5, but it also divides 3. The only divisors of 3 are 1 and 3. And only of those two, only one is equivalent to 1 mod 5. Everybody agree with that? So there's only one of these two. Okay. This one is actually a pretty straightforward example. In the following sense, I'm going to count elements. There is one and only one Sylow 3 group, right? This accounts for blank elements of order 3. Right, because I know my Sylow 3 subgroup is cyclic of order 3, right? How many elements in that Sylow 3 subgroup have order 3? So you've got a cyclic group of order 3. How many elements in that cyclic group of order 3 have order 3?
Just the one,
What's that?
just the one, the highest element in that. Or,
Actually, the other way around. All of them with one exception. Right. 3 elements, 2 of them are generator. Like use either one, A and A inverse if you like. And then you've got the identity of order 1. Right? Because every element in a group of order 3 has to have order either 3 or 1. And the only element that has order 1 is the identity. Right? So everything else has to have order 3. One Sylow 5 subgroup. This accounts for blank elements of order 5. What do you think?
that makes sense.
Right, one less. In the group of order 5, everything has to either have order 5 or 1. Only one thing has order 1, the other 4 have order. Okay. So let's kind of take inventory here. What do we have here? Well, I've got one element of order 1 in this group, the identity, right? I've got 2 of these. I've got 4 of these. This accounts for 7 elements. How many elements are left over in my group of order 15? Everybody agree with that? Let X be one of 8 left over. What's the order of X? It has to be order 15 because the order of X has to divide the order of the group, right? What are the divisors of 15? 1, 3, 5, 15. Everybody on board with that? Well, we've counted everything of order 1. There's only one Sylow group, 3 groups, so we've counted all the elements of order 3. Only one Sylow 5 group, we count all the elements of order 5. This leaves that as the only choice. one of those 8 elements, in fact, all of those 8 elements left over have to have order 15. So what can you say about any group of order 15?
It's 8 elements.
Right, so in particular, what's the structure of it that's particularly nice? If it's of order 15 and it's got an element of order 15, it must be cyclic. So G is cyclic. And if you like, it's isomorphic to Z15. So there's only one group possible of order 15, as a matter of fact. Okay. Any questions on that? Let me give you another application here. But first, I'm going to need a definition. I may have told you this before. But recall a question mark in case I didn't tell you. G is simple. Anybody, does anybody know what a simple group is? Maybe I didn't tell you. A group G is simple if the only normal subgroups. By the way, somebody give me 2 automatic subgroups of G that are normal.
So
That's right. In any group G, the identity subgroup always normal. The group itself is always normal in itself. Those are the 2 silly cases. Yes.
Can you step back for a second? Can you go over that, how you got to G is cyclic? I've been thinking about that.
Well, because we know that the order of G
Okay,
is 15.
yes,
We know this element that lives in G is of order 15. Right?
okay.
So this element X generates a subgroup of G of order 15.
Oh.
So the whole thing, right?
Thank you.
Other questions? So a group is simple if its only normal subgroups are the silly ones of G are itself and the identity. Anybody give me an example of a simple group? I'll give you, so actually a simple group is abelian if and only if it's a prime order. Right? So if you look at Z mod P, that's always simple because in fact, the only subgroups are itself in the identity, period, right? Because the order is P, any subgroup has to divide P, so it's either the whole thing or the identity. That is the only abelian subgroup. It turns out there's lots and lots of simple groups. The alternating group is simple for n greater than, so A5, A6 and higher are all simple. So is A3 technically. Certain matrix groups are simple. Why do we care about simple groups? It turns out, toward the end of group theory, I'm going to give you kind of a brief overview of this, but it turns out that groups that are simple are building blocks of all groups. You can interpret it that way. And so it was a big push in mathematics between the 60s and probably close to the 90s to understand what all simple groups look like. Right? This was a great undertaking because the idea in finite group theory is simple groups are the building blocks of basic groups. So if we understand what all the Lego pieces look like, if I've got all my Lego pieces, I know in a certain sense what I can build with these Lego pieces. So there was a big, from probably the 50s or 60s to the probably 90s, a big classification of all the finite simple groups. Well, I'll give you some of them. Z mod PZ, Z mod P where P is a prime. That's the abelian ones. The alternating groups, AN, certain matrix groups, groups of Lie type. It turns out that there's these lists of infinite parameter groups, like the alternating group, certain matrix groups, et cetera, that are the simple groups. And then there are exactly 26 groups that are simple that don't fit into any of the families. And those are called the sporadic groups. And it's really weird that there will be exactly 26, but that's the way it works out. Anyway, so the moral is these are fundamental objects in group because they are in certain sense the building blocks. You can build other groups from them. So this kind of, I've used this to kind of justify my next example. Show that there is no simple group of order 8. Which is 2 to the 4th times 5. Let me, before I start off, let me point out, note, if P in G is a Sylow P subgroup, I might ask you to prove this for me later, but now we can take this as a fact and I'll talk you through it. Then P is normal in G if and only if P is the unique Sylow P sub. Right? Because why is this true? Well, if P is normal in G, then when you conjugate P, it's still P. And all the Sylow subgroups are conjugate. So that means there can only be one, right? On the other hand, if there's only one P subgroup, right, when you conjugate it, it has to be another piece of Sylow P subgroup. But if there's only one, it has to conjugate to itself. So it's normal, right? This will be useful in this problem. So we have the order G is 2 to the 4th times 5. And let's suppose the G is simple and try to obtain a contradiction. Okay. We'll let NP as before, number of Sylow. So this will be my notation. Okay, so let's check this out. What are the possibilities? The number of Sylow 2 subgroups, and don't look at it's a Sylow 2 group because the prime is 2. Any Sylow 2 subgroup of this group will have order 16. It's a big clunky mess with 16 elements in it. So the number of Sylow 2 subgroups is equivalent to 1 mod 2. That's not really that useful, right? That just tells you that N2 is odd. And it divides 5. Now, unlike the previous example, we now have 2 options. Either one of these fits that bill. Everybody agree with that? So there's 2 options there. How about this? In this case, the number of Sylow 5 groups that has to be equivalent to 1 mod 5, and it has to divide what's left over, which is 16. Yes,
Can you explain where the 16 came from again?
right. This is P to the A times M, right? And so it's gonna be 1 mod 5, and it's gotta divide, in this case, the M, what's left over from the power of 5 is 16. Well, let's see, the divisors for 16, 1, 2, 4, 8, 16. I think we can all agree on that. And we should ask ourselves this, which one of these are equivalent to 1 mod 5? Yes.
Is that supposed to be n sub 2 or n sub
Oh,
5?
I'm sorry, yeah,
Okay.
okay, 5. Which one of these are equivalent to 1 mod 5? Well, the 1 always is. That's going to be a choice. Nope, 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 yep. Everybody agree with it? Okay. How does this help us? Well, let me make the observation that if G is simple, then N2 is 5 and N5 is equal to 16. No choice there, right? Because if either of these is 1, that means that the Sylow group is normal and it's not simple, right? So for this to be simple, you can't have any normal subgroups. That means you have to have 5 of these and 16 of these. Agree? Now, counting the elements in the Sylow, so you've got 5 Sylow 2 subgroups of order 16. How many elements does that make up? I've got no idea. This is complicated to count because if I have 2 Sylow subgroups, both of order 16, the first question is, when you're counting sets, you got to know how they intersect, right? And if you have 2 different subgroups of order 16, they could intersect in a subgroup of order 1, 2, 4, or 8. And I don't know the answer to that, at least not at this point. On the other hand, counting elements from the Sylow 5 groups are easy. Because as opposed to the Sylow 2 groups, the Sylow 5 subgroups are cyclic of prime order. So if I give you 2 Sylow 5 groups, they're either exactly the same or they intersect only in the identity. Everybody agree with that? Because the intersection of 2 subgroups of order 5 is a subgroup, and it's either got to have order 5 or 1. And if it's 5, it means the 2 groups are the same. Agreed? So any 2 Sylow 5 subgroups intersect trivially. Trivially means only the identity if distinct. So 16 Sylow 5 subgroups accounts for 16 64 elements of order 5. Right? Because each one of those 16 Sylow 5 subgroups gives you this flowering of 4 different elements of order 5, right? All 16 of them have 4 different, and 16 times 4 is 64. Everybody agree with that? In our group of 80, I've counted 64 elements. This leaves exactly 80 minus 64, which is 16 elements left in G. And how big again was the Sylow 2 subgroup? It had exactly 16 elements. So there's only room for one Sylow 2 subgroup. This contradicts the fact that we had 5 of them So G cannot be simple. So no simple group of order A. And this was a slightly more sophisticated counting argument, but not too bad. Okay, any questions on this? Okay, so let me, we're gonna move to the proof of the Sylow theorem. I am going to give you the following. Let's record the following lemma. I'm gonna need this one piece here. It's 0.13. This is a tool that I'm gonna need. Sylow theorems. Let P and G be Sylow P subgroup. So it's maximal in that regard. It's a maximal P subgroup. If Q is any P subgroup of G, then P intersect Q is equal to the normalizer in G of P intersect Q. This is a little technical limit that we're going to need. What this says is the intersection between the Sylow P and some other random P subgroup is no different than this perhaps bigger normalizer in G of P intersecting Q. You don't pick up any more elements of Q when you expand to the normalizer. So P is always in its normalizer. So we certainly have this. So it suffices to show the other containment. Containment. We show that the Q intersect the normalizer is contained in P. Because if this is the case, if this thing lives in P, when I intersect this with Q, then I will get this other containment that this thing contains this, right? So it will suffice to show that much right there.
Okay.
And our strategy to this would be, so our strategy, our approach here so our strategy will be show that P times I'm going to show that this product of two groups is a P subgroup of G. And of course, if it is, it contains both of the pieces of it. Then P and GP intersect Q is a P subgroup of G containing P. So my strategy is I'm going to show this is P subgroup. notice that if it is, it certainly contains P, right? Because P is a piece of this. And so if this is a P subgroup, that contains P, that means that, P is equal to P. Why do we have this equality? Because we know that this thing is contained in this, but this is a maximal P group. So if this is a P group, you have to have equality, which would imply that in GP intersect Q is contained in P, which is what I want to show. That is going to be our strategy. We will finish this off and then tackle the Sylow theorems next time. Any questions? Questions? All right, I will see you folks then on byproduct.